Hi, it's Mr. Canada here, and we're talking about the change of base with indices today. So changing the base can help us simplify numbers, mostly as we can use law of indices to cancel out a new common numerator and denominator. Okay, so sometimes they just ask you to change the base, like we have for the first couple examples. Other ones, you'll see where we start to use this change of base to really help ourselves out without a calculator. Okay, so this is largely used for non-calculator methods to have how to simplify and solve indices. So represent 4 to the power 3 as a base of 2. Well, that just means that we want to represent, it looks weird, but let's just consider how do we represent 4 as a base of 2. So we want to say 2 to the n equals what we were given, right? Equals 4. So either you can take the root of one side if you just know them, but typically if you're doing that, you already know, so it's not a guess and check, right? So they're going to make it something where you can actually do this. So here, we know that 2 squared is equal to 4, so we know n has to be equal to 2. So that means that I'm going to say that this is 2 squared, right? This 4 is 2 squared, and now I put brackets, and I'm going to uncover what my index was because I totally made it so I couldn't see. So now we're putting it to the power 3. So notice that inside the bracket is just our base, right? That is 2 squared is that base of 4. So we haven't changed, and that 3 we haven't changed on the outside. So we now just have to apply one of our laws, which is our power law. So 2 to the power 2, and then we do 2 times 3. So 2 to the 6. Okay. So notice we have a base of 2. Our power just changed, right? So represent 3 to the 6 as a base of 9. Well, what happens if we have to go the other way, right? We have 3 to the 6, and we want this as 9. So how exactly do we get 9, right? Well, 3 squared, 3 squared is 9, right? So we know we're going to have to we have to break this up. So here we can write 3 squared times by 3 squared times by 3 squared, right? And that's all 3 to the power 6, right? So this one you can think of a breaking up. You can do easier methods. I just want to kind of show you where this comes from. So here, what is that? That's 9 times by 9 times by 9. So really, then we can state it as 9 to the power 3. So it's just going the opposite way. Okay. So you could think it as what do I have to do to here? How do I get from 9 to equal to 3? Right? 9 to the what? 9 to the 9 to the half, right? So I had to take the square root, so that way I took a half of each of these exponents in the power law. Okay. So here, simplify this, right? So what do I notice? I notice I could represent everything in the base of 2. I could represent everything in the base of 4. I could represent everything in 16, because they're all numbers, right? They're all just numbers that are 2 times 2 times 2, right? All in that 2 times table. I'm going to choose to make them all the base of 2 because I often find it's easier to do stuff like example 1, where you're going from a bigger to a smaller, rather than a smaller to a bigger. So that means I'm just going to start writing my bases out. So I have 2 squared is 4, and I'm just going to put the indice up top. Then I'm timesing by, well, 2 times 2 is 4. So just on your fingers, you can even count the indices you're using, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 2 to the power of 4 is equal to 16. And then we have to square this. And lastly, let's write this as 2 to the 9. Okay? So here, we're just applying our power law again. So 2 squared, all to the power of 3, will become 2 to the power of 6. This will be 2 to the 8. And then this is all going to be over 2 to the 9. So we can add our top our top indices, right? Because it's multiplied with the same base. So we get 2 to the 14 divided by 2 to the 9. And this will give us 2 to the 5, which we could state as 32. Right? So we were able to muddle our ways through not using a calculator just by using a little change of base, right? And then just using the idea that we can use all these laws of indices to cancel out. And I say laws of indices because it's kind of confusing sometimes to say it's the law of indices. Okay, now this one, really confusing, but there's a little bit of subtle tricks being kind of put in there. Not necessarily all on change of bases, but just little subtle tricks. So, what exactly can we do? So, one thing I'm going to show you, and I want to just put one of these examples in somewhere. If we cancel out one of those from here, we can cancel out one of these from here. If we cancel out an x plus 2 from here, we can cancel out an x plus 2 from here, and we can cancel out an x from there and an x from there. What we're left with is 3 plus 1, right? Because we cancel out an x and an x plus 2, so we just have 3 plus 1 on top, but on the bottom we have x minus 2 here. Okay? So, only way that we can kind of simplify this is we can say 3 plus x minus 2. Because I just multiplied that over. So it's not really a change of base. I just wanted to show you a different kind of simplify, which of course we can leave as 1 plus x. So sometimes I'm just going to throw random questions in at you. Just be prepared for anything. Okay, so here's 9 little questions for you to try out. Some of them are a little bit more challenging than others, so if you get stuck, just skip it and move on. When you're ready, press play and we'll go through the answers. Okay, so once again, I've said that I like going from a bigger number to a smaller with my change of bases. So 16 squared, I know I can write as 4 to the power of 4. So this is going to be 4 to the minus 2, which is 1 over 4 squared. Whichever way, just either one are suitable because they just ask for us to represent as a single base. Here, I know 5 times 5 is 25, times 5 is 125, so this is this bottom part, I'm going to put as 5 cubed. That's going to be all squared, and this will be 5 cubed. So I'll be left with 5 cubed over 5 to the 6, which is equal to 5 to the negative 3. Okay, next one, once again, I'm just going to convert my base in the bottom. So 2 times 2 to the power of 3 is 8. All to the power of 3. So we'll get 2 to the power of negative 1, or 1/2. Okay. Next, this one, we could do one conversion and get that 3, right? But what I notice is it's not really an even number, so we're going to get something not as nice. I want to still work with my 9s, even though I have to do 2 of them. Because if you've noticed, I've just been doubling these, right? When I do 3 squared. So I'm just going to make that connection. Because you don't have to show all of your work with indices. So we got that. And then we can simplify. On the top, we'll have 3 to the power of 6. On the bottom, well, we're just going to add those together. So we're going to have 3 to the 3. And we're going to subtract our indices. 3 to the power of 3. Which is also, well, 3 times 3 is what? 3 times 3 is 9. Times 3 is 27. So, and actually, I kind of want to just go back and do these. So if we can state this. Well, actually, I'm just going to leave that, sorry. Because I do notice it does say, I did state that, hey, we should write as a single base. You know that you could solve these out pretty easily. So here, 625, how do we write that? Well, that's 5 to the power of 4 times by 5 to the power of negative 3 over 5 to the 7. Careful with those negatives, they sometimes look hidden. So the top we can simplify to 5 over 5 to the 7. So we're going to subtract those and get 5 to the negative 6. This one, once again, looks a little bit more challenging because we have 3 kind of bases multiplied and none of them are the same. I'm still going to get them all in terms of 3. So like I said, I like working this way because I know my times table is better than my divisions. 3 times 3 is 9, times 3 is 27, times 3 is 81, so this is 3 to the power of 4, and this is, well, 3 times 3 times 3 is 27, so this is 3 cubed to the negative 2. Simplify this down, so I'm going to combine the first twos. We'll get 3 to the power of 10 times by 3 to the negative 6, so in the end we get 3 to the power of 4. Moving on, keep getting them in terms of 2, so we're going to have that as, well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, so 2 to the 5 times 2 is 2 to the 10. Then we're dividing by 2 to the 6, and all of this will be divided by after 2 squared. So we're going to get 2 to the 4 divided by 2 squared, which is 2 squared. Okay, so keep on going. First off here, I'm just going to get rid of all my brackets and get everything onto the same side. I notice that they're addition. So 16x to the 6 plus, make sure to bring that 3 onto the 2 as well, because there's a bracket around everything. And then subtract 4x squared. That has to equal 0, right? Because it is an equal sign. So what exactly can we do here? Well, I noticed that these two are the same, right? So I can write, well, 16 and 8 is 24x to the 6, right? And we have this minus 4x squared. So I can't really actually combine those at all, right? All I could do is do a little factoring out and a little canceling. So I can write this. I can divide everything by 4 to get rid of some of the coefficients, but this is about it. So here, divide the 4, so we get 6x to the 6 minus x squared equals 0. And then I can divide by x. I can divide by an x squared term everywhere, because it doesn't matter that we're dividing 0 by x squared, it's still 0. Right? So here we have 6x to the 4 minus 1 equals 0. And then if we really wanted, we could solve for what x is, right? So that's where indices can kind of help us for solving. Here, okay, looks really messy, but when we expand brackets, it usually turns into a lot nicer. So let's work in that top part. We get 4x squared plus 4x plus 1 minus 1. So right away, I'm just going to cross out these. I know I don't want to see them in the next part. Now here we're dividing by 2 to the 5x. So what can we do? We can write these all in with the base of 2. So we're going to write 2 squared and x squared plus x divided by, and yes, I factored that at the same time. So noticing, I can subtract those and I get 2 to the minus 3. And I'm actually one thing I'm going to notice and point out here, I have an x here and an x here. So I know I can factor out an x. And I'll be left in the inside with x plus 1 all over x. The x's are going to cancel. And so finally I'll be left with 2 to the minus 3 x plus 1, and I can state that like that or remove the brackets, all up to you.